now it's like towards the the middle of the semester. We're pretty much, after we cover these things, we will talk about cryptocurrencies, and also we will start to do some paper reading. And what we will do is that we will give you guys like 200 papers to choose from. So starting from next week, you guys will be looking at the papers, because I mean the really cutting edge research papers, because when we already covered so many topics, it's I guess most of us have enough knowledge to directly read those research papers, and then you guys can find anything you like. So it will be a big pool of papers to choose from. There will be a lot of them are application oriented. There's some hardware stuff that can be really mathematical as well. So it's really it has big diversity. So if you guys are interested in math, there will be a lot of papers to choose from. If you guys are interested in how to apply those things or how to implement these things in real applications, there will be a lot of them to choose from too. I will give you guys two major conferences to choose from. Those are one of the most important, most impactful research conference in the area of security. Actually, I can give you guys some information. The two most impactful security conferences are, one of them is called we usually call them Oakland. It's called Symposium of Security and Privacy, which is held in Oakland, California. So we usually just call it Oakland. This is Oakland is the Oakland where the Golden State Warriors are located in California. Okay. And then there's another one called CCS, Communication and Security, something like that. Conference of Communications and Security. These are this is held in DC, so it's in the East Coast. Actually, the two most important conferences, one of them is in East Coast, the other is in West Coast. And you guys will have a lot of time to read those research papers. And then I'll also set up a Google form, so then you guys can choose your topic and presentation time. Yeah. And according to our past experiences, most students prefer later times. So we will, in order to encourage the students to present earlier, we will give some bonus to the students who choose their presentation time to be a little bit earlier. So yeah, that's pretty much what it is. And then we will only have one written exam, and after that it's just paper reading. Okay. So and the other thing is, there is a big difference between security and cryptography. So far, what we have covered is on the topic of cryptography. Later, we will really get to the topic of security. So security is more application oriented. So it's not, when we mention security as this type of research topic, usually there's very limited math involved. So when we are done with this math, then there's pretty much no math at all. And then those people, when they're doing research in the area of security, they usually consider various types of attack, because it's really significant that how many attacks can be launched on the internet. For example, like now the Ukrainian war, if you guys know, there's a really famous hacker association called Anonymous. Maybe you guys have already read the news about that, right? After the massacre of Bucha, which took place 2-3 days ago, the Anonymous association, they actually found all the information of the troops. There are like 120,000 people. Their name, their ID, their information, their address, whatever it is, and even their wives and children, they're just completely open. So those people, they're really, they're really powerful in hacking all this type of information. And then those who were actually they were participating in the Bucha massacre. Their information are all online. So there are really a lot of information you can get from the internet, and then those people, they're really, the Anonymous Association, they're really, really powerful. Okay. Now back to the signature scheme. So let's first look at our first signature scheme. It's also one of the most widely used, the RSA signature. Okay. In short, the RSA signature scheme is pretty much like this. You encrypt. Instead of encrypting a message, you decrypt the message. That is its signature. Now think about this. Encryption is that anybody can encrypt because anybody has the private key. The goal is for the user to decrypt, right? Using the private key. So only the legitimate user can decrypt the message. But signature is different. It's almost the exact opposite. The goal is to let everybody to be able to verify your message. So what you do is you actually put your private key as one of the input, okay, and then let anybody to use. Put your and let everybody use your public key to recover the message, which is identical to decrypting the message. Okay, but there is some difference. The difference is here. We actually apply another function. This is called a redundancy function. Okay. So why do we do that? That's because there is a property. That's because there's a property that we want to destroy that. This property was thought to be inappropriate in old times. However, in recent years, people's ideas about this property has been changed. So let me tell you guys what this property is. This is called the homomorphic property. Homomorphic property. Okay. Now RSA has this homomorphic property. So what is the homomorphic property? That actually means if we just disregard this redundancy function, okay, this R, just think of this Rm as nothing changed. Just think of this Mr as the identity mapping. Okay, think of this R as an identity mapping. So this M is equal to Rm. And then what is your signature? S is M. Okay, no R. MD. Okay, so the signature S is M, and then D is a private key, right? Mod N. So D is private key. What happens? Okay. Well, think about this. Suppose there are two messages. Okay, one is called one is called M1. Okay, and then you sign it using D. And then there's another another message called M2. Okay? And it's also signed with the same private key. Yeah. And then the signature is S2. Right? Okay. What if we multiply S1 by S2? So if you multiply S1 by S2, this is equal M1D, okay, times M2D, right? Mod M, which is exactly the same as M1 times M2, D mod M. Okay. This is called the homomorphic property. Okay, you may ask, what does that mean? I mean, you multiply two messages, M1 and M2. So what are these messages? Maybe they're text files, right? Anyway, in order to apply RSA, you have to convert it into an integer, okay, between 1 and n minus 1. So it's an integer. And then there's another message called M2, and then you just multiply them. So you have two messages. They are most likely originally text files. And then you convert them into numbers. And you multiply those numbers. Does that make any sense? So it may not make any sense. But anyway, even though it doesn't make any sense, what you do is you can create a signature. And this signature is valid, but you have no control over this message. You don't have any idea what it is. Right? You multiply two messages. What do you yield? Most likely it's gibberish. Okay? It's totally random. So, well, then we can think of it. This is kind of like the this existential forgery. So, in other words, the adversary can always create messages by multiplying old signatures, right? To create a valid signature. But he has no control over the message because he has no idea what, the product of two messages actually mean. So that's existential forgery. Anyway, in old times, people traditionally think this is not good because we have this is regarded as one of the weakness of RSA signature because of this homomorphic property. You have existential forgery. That's regarded as a bad thing. But now things changed. Anyway, let me elaborate on what does homomorphic mean. Okay, because there's in math there's something called homomorphism, right? So let me briefly explain what that means. So homomorphic property. Why is it called homomorphic property? It's because if we regard this message as, for example, like in a ring, or maybe group. Let's talk about group homomorphism. Group. Usually we use this type of notation to represent a homomorphism. So homomorphism is, what does that mean? Homomorphism preserves operations. So you can have homomorphisms between many mathematical mathematical structures. So depending on what structures you're talking about, then you have different concepts of homomorphism. For example, if you're talking about group homomorphism, then there's only one operation, which is called multiplication. That's this case. And then if you talk about rings, there may be two operations. Right? If we talk about fields, there are four operations. They have to preserve this type of operations. And there can be vector space homomorphisms too. In that case, you have to preserve both the addition, vector addition, and scalar multiplication. So depending on what you're talking about. So here in this case, let's think of the signature. Take the RSA, for example. Let's think about this. So when you have a message, this message is called M1, right? Okay? And then it's mapped to the signature. The signature is M1 raised to the power of D. Okay. And then you have another message M2, which is raised to the power of M2D. Now, if we think of this M1 and M2, this message, it actually forms a multiplicative group. But we just have no control over the meaning of it. It won't make any sense if you multiply two messages together. But it doesn't matter. It really preserves this property. So even though we have no idea what this means, you can consider the multiplication of two messages anyway. Okay? But then you have considered the multiplication of M1 times M2, even though it doesn't make any sense. Then this is mapped to M1D times M2D. So as you can see, this operation, okay, this operation, multiplication, is preserved under this mapping, which means if you multiply them first, okay, and then do the mapping, it's going to be the same as you do the mapping on these individual elements first, and then multiply them. So this operation is preserved. This is a group homomorphism. Okay, this is a group homomorphism. It has the homomorphic property. So then they actually took the idea from algebra and called this a homomorphic property. Now, they think this existential forgery is one of the weak points, and then they want to eliminate that. How to do that? We can add another function. This property can be destroyed using a very easy mapping, a very easy function. So let's add another function here. So instead of mapping M1 directly to M1 to the power of D, we apply this M1 into a function first. So this becomes Rm1, okay? And then we apply this first. So in this case, if you apply, this extra function, it will very easily destroy the homomorphic property. Okay, this function can be very easy, and then this function is purely arbitrary. So the goal is to destroy the homomorphic property. You can simply choose an invertible function, a very easy invertible function, whatever it is, linear, nonlinear, whatever, as long as it is invertible. Okay. So it's a redundant function because the sole purpose of this function is to destroy the homomorphic property. So that is why it's called a redundancy function. So whatever function it is, addition, multiplication, linear, whatever, nonlinear, whatever. Okay. So now the signature generation algorithm becomes, okay, you apply the redundancy function first, and then you raise to the power of D. The verification is you get this MR first, okay, from by doing its what is it called, the modular exponentiation with the public key, and then you recover the message. Okay, so that's the idea, homomorphic property. Later we'll talk about something called homomorphic encryption, because the cryptographers' ideas changed over these years. So instead of regarding this homomorphic property as a weakness, now they even thought this may be a good thing, and then they design systems that has this property, okay, and they make use of this property. So that is called the homomorphic encryption. So we'll talk about that later when we cover more topics. Anyway, this is RSA has this homomorphic property. If you don't want it, then you apply the redundancy function. Okay. Let's take a look at the RSA signatures characteristics. Okay. what are the attacks? Number one, integer factorization. Number two, homomorphic property. So homomorphic property I already mentioned. This has existential forgery problem, okay? Which may not be a problem because you have no control over the message, okay? Reblocking problem. Let me explain this. So what is a reblocking problem? Okay, so the thing is, why do we need to use signature? Because we want to make sure that the entity we're dealing with, we're communicating with, is authentic in order to prevent the man-in-the-middle attack when we do key management, right? So, in other words, signature is often used in conjunction with key management schemes. So it's very natural. So you need at least two. A signature scheme and a key management scheme. Let's think about this way. Suppose for both systems we use RSA. So we use RSA signature, and then we also use RSA key management. So in each RSA, you will have an n, okay, which is a product of PQ. So for each RSA, you have a mod n something. Now, inevitably, you will be handling two moduli. Okay, that could be a problem. Why? Because you mod something and then you mod another number again. One of them has to be smaller. Okay, if you mod a big number and then mod a smaller number, or you mod the smaller number and then you mod a big number, sometimes you have a problem. So that is called a reblocking problem. A very easy example is, let's say, what you do is you can, for example, you mod, let's see, we mod 10 first. Okay. First we mod 10, and then we mod, for example, mod 5, and then see whether we have any problems at all. Okay. So let's see. So initially, for example, x is something like, okay, x mod 10. And then what you do is you do mod 10, and then you mod 5. Mod 5. Or maybe mod 5 is not a good example. Maybe mod 7. Okay. Is that okay? So let's see. So let's say initially your x is from 1 to 10. You have 9, right? So 9, what you do is you do mod 10, then you still have 9. And then you mod 7. That becomes 2. Okay? When you recover, okay? So when you recover, you know the mod 7. You recover, then it is 2. And then you recover in mod 10, you get 2. That's a problem. Okay, so when you mod a big number and then you mod a smaller number, you have a problem. Right? Sometimes you have a problem like this, because this limits your number. This limits your number 9 between 0 and 7. So you lose some information. The problem is this part you lose information. Okay. Well, if you do it the opposite way, let's see. Okay, so if you do it the opposite way, you 9, you mod 7 first. Mod 7. So you have 2, right? And then you do mod 10. So this is what you do. You also get 2. But the thing is, initially 9 is considered the same as 2. Okay? The thing is, this part, you lose information. Info. But this part you don't. You don't lose any information at all. Okay, so here, well, it looks like 9 and 2 are not the same. But when you're applying your first system, 9 is considered as the same as 2. So you're not losing any information at all, right? Because in your first system, we already have a limitation on the information. It has to sit between 0 and 6. So 9 is already filtered out in the first phase. You're not losing any information when you apply the second modules. So in other words, this one is you have a problem. The problem arises if you mod a bigger number first, and then you mod a smaller number. No, then you will have a problem. Okay. If you mod a smaller number first, then you're okay. You don't have the reblocking problem. So that's it. So the reblocking problem, in short, is when you apply the second mod, it loses information because the first mod is bigger. And the importance of redundancy function is also put into an ISO standard. So this is used to destroy the homomorphic property. Okay. RSA signature's performance is also pretty good, as RSA is really good. Okay, so it's no problem. Now let's move on to the Elgamal signature scheme. This Elgamal signature scheme has absolutely nothing to do with Elgamal encryption algorithm. Okay, it's a very tricky signature scheme. It's also carefully designed. Unfortunately, Mr. Elgamal, I should say Dr. Elgamal, was not very lucky because his encryption scheme, both of his encryption schemes and signature schemes were really well designed. However, the encryption scheme came after RSA, so it's never used. And their signature scheme is a strong competitor of the RSA as well. However, it has a better improvement called DSA, which is based on Elgamal signature scheme. So there's a stronger competition. So the Elgamal signature scheme is almost never used. Unfortunately, he's just a really unlucky guy. He has designed two really powerful systems, powerful algorithms. Unfortunately, none of them are widely used today. Okay, so let's take a look. It's a pretty tricky way to put things together. So may not be that easy to understand at the first sight. 这个蛮可惜的 Elgamal 的这个 signature scheme 呢，很可惜哈。但是它其实是一个非常巧妙的一种凑数字的方法啊，所以一开始同学们看起来可能没有那么的容易理解，它就是凑得很巧，真的是很巧。我们等一下讲就知道，这些证明也不会到很难，但是就是非常的巧，凑出数字出来。那这个虽然没有用，可是我们把它的这种凑数字的方式哈。如果已经理解了，那就很容易理解 DSA 到底在干什么。我们等会讲 ，DSA 就真的是 RSA 的一个非常强的一个竞争对手。所以 signature 基本上就是 RSA 跟 DSA。那 DSA 它还有一个比 RSA 更强的特性，是它可以直接移植到 DSA， 可以直接移植到椭圆曲线上面，这点 RSA 是做不到的。所以说它可以移植到椭圆曲线上面，就代表说它可以在行动装置上面使用，速度是快很多。它可以用在手机啊，甚至什么呢？你甚至这种所谓嵌入式系统都有办法使用。然后甚至未来比方说像这种晶片卡甚至都有办法。那你说晶片卡这么小的这种运算能力，可能都可以用啊，这是它 DSA 一个很强的一点。那它有它的缺点呢，凡是用在椭圆曲线上面就有个缺点，就是它没有什么弹性，它的参数选取没有弹性。但是呢，瑕不掩瑜啊，因为说实在，你也大部分情形之下，你把标准定出来就好，你也不太需要那么多弹性。那它就是有一些固定的那些参数，就是你只能去选那些固定的参数。有时候你想要把它的，比方说安全性那个 key 长度提高一点，不行，对你就是那些长度，你就是不太能动，就这样，没什么弹性。那没有什么弹性，不算是一个太大的问题啊。所以说它就是现在行动装置来讲 ，DSA 还是最主要竞争者。OK， So let's take a look. Let's take a look at the algorithm signature scheme. It's a really tricky way to manipulate these, mathematical objects. So maybe a little counterintuitive because we don't. Maybe at the first sight you may not know why they put these numbers together. But let's just take a look. Okay? The key generation is similar to the algorithm encryption algorithm. So it's based on the discrete log problem, also based on the group ZP star. It's based on this group. Okay. Say ZP star. Okay. So similarly, the message sits between 0 and p minus 1. Now the key generation is the same. We first choose a p. Okay, so we choose a p, then we'll have a ZP star. P is prime. Now, this alpha is a generator of this group. Choosing generator is a big deal, but we omit this. Okay. Anyway, there is a method to choose. Okay. So that's the idea. Maybe I can elaborate a little bit more on this. Okay. So I hope I can give you a good example. Maybe let's see. Let's see. We'll do some calculation, concrete calculations. Let's choose a number which is not too big, not too small. So not too small, so that it's not that trivial, and then we can have some idea. Maybe 13 is good. Let's take a look. Okay, so 13 this number is not too big. Okay? It's manageable. So let's see, p is 13. Okay, and then we have to choose a generator. We're not sure whether a number, when we look at its powers, it can actually cover every element of Z13. Let's see. So anyway, we have these numbers from 2 to 12 to choose from, right? We certainly won't choose 12 because 12 is minus 1. Obviously, it won't. If you consider its powers, it won't cover everything. Maybe let's take a look. Okay, so for example, we choose 12. Okay, what will happen? Because 12 is actually minus 1. Right? What is the powers of minus 1? So 12, if you look at powers, 12, the power of 1, 12 the power of 2, 12 to the power of 3, and so on and so forth. What you do is you're actually considering the powers minus 1. So the powers of minus 1, it will alternate between positive 1 and minus 1. So will it be able to cover all 12 elements of Z13? Certainly not. Okay, because 12 to the power of 1, this is minus 1, right? And then 12 squared must be 1. 12 squared must be 1, and then this must be minus 1 again, so, because it's alternated between minus 1 and the positive 1. So the powers of 12 only cover 2 elements. So definitely this cannot be a generator, right? So let's just run now. Between 1, we have 1 to 12 to choose from. So we don't know which one can be a generator. Okay, we know that 12 cannot be. How about 1? Definitely not. Okay. For 2, we don't know. Let's see. Okay, so let's see. We consider the power of 2 and then see whether or not we can cover everything. Let's take a look. So 2. Okay. And so this is 2 to the power of 1 to the power of 2, which is 4. Let's see. 4, okay? And then 8, this is okay. And then 8 times 2, which is 16, mod 13, so we get 3. Okay, so this is 2 to the power of 4. Okay? And then 3 times 2 is 6. Okay, so this is 2 to the power of 5. And then 6 times 2, okay, 12. 12. Okay, 12 times 2, 20, like 24, okay, 13. Okay, so this is 11, right? This is 11. 13, 11. And then 22 minus 13 is 9, right? 22. So then we have 18. 18 plus 5. Yeah, it looks like we already, this actually really the powers of 2 covers everything. Then, yeah, 10. Get 10. So it's 5, 6. This is 7. This is 2 to the power 7. This is 2 to the power 8. This is 2 to the power 9. 2 to the power 10. 2 to the power 11. So let's see. Which is 20. 20 mod 13. 7. 2 to the power 11. 2 to the power of 12. 2 to the power of 12 is 14. Yeah, 14. Which is 1. This is 2 to the power of 12. Not really actually go back, so it's a big cycle. Okay. So this is the first time. This is the very first time that the power of 2 goes back to 1. So it covers every number from 1 to 12. Right? 1, 2, 3, right? 3, 4, 5, yeah. That's pretty good. That's a good example. So maybe we can take a look at these numbers. So 2 to the power, so we do have this 2 to the power of 12. Let's see, equal to what? 好，这个时候我们就可以看一下，我们来看一下这个例子啊，来2的1次，2的2次。So we can take a look.好，这边我们随便选一个2，然后我们就看它的次方，它就真的是1到12全部出现一次。对，那这个时候呢，我们其实可以看一下。你如果乱选的话，如果你随便的选啊，因为你不晓得谁会可以全部走完嘛，对不对？那我们可以看一下谁可以走得完。So if we just randomly pick any elements, is it possible to go over the whole group? So that actually depends on this index. If this index is relatively prime with 12, then you're good. So the thing is, we look at these numbers because now we can represent every number as a power of 2. Okay, so let me give you an example. Let's see if we choose this. This number is 8. Is it possible, if we consider the powers of 8, is it possible to visit every number from 1 to 12 exactly once? Actually, the thing is no. The reason is if we consider 2 to the power of 3, this can be regarded as every time you go 3 steps from 2 to the power of 1. Instead of going 1 step, you take 3 steps. So it's clockwise. The thing is, if you do take 3 steps, the next time its square will reach here, 2 to the power of 6, and then it will reach 2 to the power of 9, and then it will reach 2 to the power of 12. You end up with a shorter cycle. You guys know what I mean? So the thing is, just because this index 3 is not relatively prime with 12, if you consider the powers of 8, you end up with a shorter cycle. 所以这简单的说呢， 我们今天你不晓得挑谁可以走完全部，但是我们只要挑一个走完了全部了，那接下来我们就知道挑谁可以走完全部。谁能走完全部，就看他的次方会不会跟12互质。只要跟它不互质的话，你会走到它的最大公因数，你的 cycle 会变小。所以你你这个8不行了，这个2也显然不行，这个就4，你选4也不行，8也不行，啊，然后呢，这个不行，5可以哦哈，那这例子还不错啊，这个不行，这个不行，不行，所以你选谁可以呢？选2可以，选6，2的5次方可以，选11可以，2的7次方跟2的11次方，就1次、5次、7次、11次，刚好选这4个。换句话说，你从1到12里面，如果你现在随便挑谁是 generator， 如果你运气好选到2或者是6，或者是11或者是7，2、6、7、11这4个，其他不行。那你的命中率是什么呢？刚好就是这个 V12，你 V12只有4个 element， 那你总共12个里面，12个 element 你随机选，你只有4个是可以当做 generator 的。那你运气好选中，你的命中率就是1/3，所以选中了，你只要猜到那就可以了啊，基本上是这个意思。所以我们在选这种 generator 的，你 P 是选没问题，大质数直接哈，我们就是 primarily test 就可以。但是问题是什么？你的 alpha 怎么选？这个就看你的运气，这样知道吗？啊，是有一些更好一点的方法是可以去选的。我只是简单跟大家讲。So actually, how to choose this generator alpha? So in this case, I just gave you a really good example. So we have all 12 elements from 1 to 12. There are only 4 numbers if you choose that can serve as generators, which is 2, 6, 7, and 11. Just these 4 numbers. And we have no idea what's their relationship. What's their relation with the number 12? We don't know. And then it's also in mathematics, it's also extremely complicated. Even number theorists don't know because there's no good theory to quantify such relations. 基本上数论来讲也没有办法知道到底12跟这4个数2、6、7、11到底这4个数字跟12是什么关系？就连数论的这些数学家们也搞不清楚。这个困难呢，也是个双面刃。它的好处是说，你的安全性就是这么来的，因为数学家就是找不到他们的什么关系。今天如果你给我12，然后我可以透过某种关系找到这4个数字的话，那这安全性就会降低了，对啊，这也是一方面是它的好处。Okay, so anyway, this is regarding the generator. How to find generator is not a trivial task. So far, what we do is we just do trial and error. There's no other. There's a better way, a slightly better way than that, but we won't cover that. There's something called Gauss lemma. Gauss. We randomly choose something, and then if we're unlucky, for example, we choose this, and then we have a shorter cycle, right? We cannot visit all 12 numbers, but Gauss lemma provides us a means to increase the numbers to be visited. So to increase this orbit. So if you keep doing that, eventually we'll cover everything, and then we can find a generator. So this is generator. Now let's take a look at the signature generation. This is really a little bit counterintuitive. 这真的有点反直观。这个如果你直接这样看它一行一行，它到底它的 signature 怎么定义你其实是第一次看的，我可以跟各位朋友保证，你一定是一点想法都没有，你完全不知道它到底在干什么。我想同学应该会有这样概念不过没关系我只能说这个东西看起来很奇怪，但是你到后面你等我去验证的时候，你会发现很神奇的是一大堆东西就消掉，然后最后答案就出来了 真的很怪。我只能说，Algamo 是真的太聪明了，他凑出这样数字。但是我会花一点时间在这个地方帮各位同学理解一下这种，因为后面的 DSA 基本上就是这个的强化版，啊，它就是这个强化版。So actually, this even though this is counterintuitive, I will spend some time on it because this is really a smart way to put things together, and then later, if you look at the next page, the verification scheme, you will just suddenly you will realize that wow, lots of those numbers they just cancel magically. They cancel each other, and then the result show up. And the DSA signature scheme is an enhanced version of the Algamo signature scheme. So it's applied even make it even a little bit more complicated. Anyway, let's see. So signature generation. First we'll generate a random key. I have no idea. So that it's this. Okay. And then we compute this, and then we compute this, and then compute this. Just lots of information, right? Anyway. Maybe we can look at the things. What are related to the message? So what's related to message? This M is the message, and then this message isn't fed directly into the calculation. Now it enters a function called H. This H is a hash function, a secure hash function, which we will be talking about soon. That's our next lecture. I also posted online as well. Okay. I think that's the lecture 10. So this hash function is secure hash, and then it's different from the hash function we have learned in database. Maybe you guys have maybe some of you have learned database before. Have you guys anybody learned database system? 有没有人学 database？database 有 hash 哦，有学过吗？啊。那个 hash 跟这 hash 还不一样，是不太一样的。我会简单讲一下，就是说它这个 hash 同样是 hash， 但是同样称之为 hash， 但是它的设计上有类似的地方，但是它的目的有一点不一样，造成它的使用上也差很多。hash， 那这个 hash 这个字中文翻译的是非常的怪。对，翻成了杂臭，我也不知道是到底怎么翻译的。Anyway, the hash function, the basic idea is that you have some input, and then you have some really quick operations added to this input, and then you get some result. And you usually in database systems, it's used to grouping. It's used to do grouping for elements. For example, I mean it can be used like this. For example, you have a server, okay, and then everybody wants to connect to the server. Well, this server will have will soon be overloaded. So you have to find a way to quickly dispatch tasks to your secondary servers. Okay, how to do that in a fairly manner is a good question. Yeah, because I mean, well, you can randomly assign, right? But how to do this, this quickly? Hash is one of the way. For example, you have like seven servers. You can quickly calculate the hash and then just get some result. No matter what this means. As long as roughly speaking, you send like 1/7 of the load to each server, then it is fair. And database also like that. I mean, you have a lot of data, and then you want to determine which piece of data is saved in which server. This can be done using a hash function as well. But that's in the sense of database. So this type of hash functions has to be extremely efficient, very, very quick, and then give you, really balance the results. But it does not have to be secure at all. Now we're talking about secure hash. So this hash although it has to be quick. But the important is first you cannot have a major weakness in this hash. For example, you cannot cause collision too easily. Otherwise, you will have a problem. Otherwise, if two messages can have the same hash, if it's easy to find those, then it is easy to create fake signatures because the signature depends on the output of the hash. Even if your signature is a good system, if the output of the hash is very limited, then you will end up with big problems. That's one reason why this MD5 hash algorithm is unused because there's a collision problem. Okay, let's take a 10-minute break. So now this signature scheme was designed in a really smart way, and the purpose of such schemes is different from designing an encryption algorithm. One of the reasons is that you really don't have to be you don't have to make every step invertible. Okay, because it's a signature scheme. The point is you must have two ways of reaching the same goal. So maybe we can think of it this way. So for an encryption scheme, you have plaintext. We think of the plaintext as a starting point. Okay, so this is plaintext, and then you have ciphertext, and then you can go go through many different steps. But the thing is, you have to find a way back, either the same way or a different way. So the symmetric crypto systems is like you go from plaintext to ciphertext, and each step is reversible, so you can reverse the process and then get back to the plaintext using a decryption algorithm. And then for asymmetric crypto systems, you come back from a different route, so that is also okay. Okay? So even though each step is not reversible, you can always come back. But the signature is different. So signature, if you think of a plaintext, okay, plaintext, and then you go here to signature, right? The idea is a little different. The point is the signature has to be verified, okay? And then this verification, you have a verification process. The verification process does not need to be the verification process. This process does not need any private key. Okay, so here this part you don't need private key, but this part is generation scheme. You need private key. So you have to have a separate two-phase thing, and then this is your final destination. So the idea is you can go from somewhere, and then the thing is this may be a one way route, but the thing is here you need private key, and then here you only need public key, and then you reach some goal. Okay. So that's the idea. So that is why the signature generation algorithm, these things this may not be really may not look intuitive. So maybe I can just write it down because later on the next page you guys can compare. So we compute R. R is congruent to A to alpha raised to the power of K mod P. Okay. And then we have this K inverse, and then we compute this S. Okay, S is equal to K inverse. Okay. And then we have this in the middle, HM plus AR. Okay. have two different moduli. Here we have two different moduli. So let me explain. So this R. R works in mod P. So actually R is this whole thing is in ZP. But S is working in a different group. Actually this works in ZP star. You can think of it as this can be thought of as this part works in the index. In the index of the generator. Because if we look at the verification, okay, this all depends on the verification. But look at the verification. The verification, this is the signature, the S, which appears on the index part of your final destination. Okay. So that is the reason why this is mod P minus 1. I'm just trying to let you guys understand this as much as possible, because we have this. If you guys remember the Fermat's little theorem, we have this. Okay, mod P. This is Fermat's little theorem. On the index part, this group is in. This is. The group is works in terms of multiplication. So this is maybe I should put it this way. Okay. This group, if we look at its index, it works in a multiplication manner. So the two indices, they can multiply together. And then if two indices multiply together, here, this, maybe I put it this way. Let's see whether we can put it this way. So let's put it this way. Okay, we have a number here, and then if this number, maybe this is called we can regard this as a ground floor. So ground floor， 好，我们比方说看这个叫做1楼好了。这1楼呢，就是在这个底部，你都是 mod P 的。那你今天上了2楼，你上了2楼，2楼就会是什么呢？就是 mod P 减1哦。为什么2楼会 mod P 减1呢？因为2楼你是跟这个 Fermat 这个有关的，它走 P 减1次会回到原点。那2楼的运算都是乘法的，2楼的加法在1楼的加，2楼的加法等于1楼的乘法，2楼的乘法等于1楼次方，这样可以理解吗？对不对？所以在2楼，你这边的你这边所有的 mod 哈，就是在指数部分，它就是 mod P 减1啊，因为它是 P 减1次就回到原点。So maybe we can think of this way. Okay, yeah. Maybe this is called the first floor. First floor. Okay, and then this is second floor. If you're on the second floor, that means you're working with indices. If you're on the first floor, that means you're just working at ordinary numbers. You're not working with indices. Okay, so we treat all second floor numbers as indices. If you add two indices together, it's the same as you're multiplying two numbers on the first floor. And then if you multiply two indices together, it's like you're doing exponentiation on the first floor. Okay? So that's the reason why we have two moduli. So one is mod P, the other is mod P minus 1. This signature will be fed into, on the second floor later, because when we verify the signature, it appears on the second floor. All right, let's take a look. This is how we verify. When we verify the signature here, this is r raised to the power of s. So this is actually, indeed, this is on the second floor. Okay? So on the second floor, that is the reason why it's mod p minus. Okay. So we can roughly take a look at the verification scheme before we come back to the signature generation algorithm, because they are designed together. So one cannot understand both if you look at them separately. Anyway, here what we need to know is that we don't need to reverse every step, but from the signature we can calculate our final destination. This is called V1. And then there's another final destination, V2. Okay? So V1 and V2, we're going to a different, we're going to the same direction, but one of them requires the use of public key. The other one does not. Okay, so maybe I can draw a little diagram like this. So this is our plain text M, okay, and then here we go from M to the signature S, right? And then finally we go V1. So this part we need public key, public key. And then this part, for this calculation, we need private key. Okay. And the thing is, here is one way to reach V1, but there's an alternative way. Alternative way is you don't need any keys at all. You only need M. So this is an alternative way. This is V2. Okay. What you need is you need the original message. That's it, right? So here you don't need any keys at all, and then you just compare them, whether they are correct. Okay. So you generate a signature. So this part depends on the private key. There's an alternative way to reach the same goal. This does not need any extra information at all. You only need M, nothing else. Okay? So this part is the verification. So this part is the verification. So the verification only needs a public key, so everybody can verify. But this part is protected because this part, from the message to the signature, this needs a private key. Okay, so that's the idea. Okay. Now, let's come back, and then let me rewrite this. So this is K inverse, and then HM plus AR, and then mod P minus 1. Okay. Mod P minus 1. Mod P minus 1. Okay. So this is S. So we'll calculate all these, big monsters. Now let's take a look. We verify the signature. So we have y raised to the power of r, and then r raised to the power of s. So y to the power of r we can calculate. So what is y? Okay. We can do a simple calculation. Let's do a simple calculation. To prove this is a valid scheme, we need to calculate whether V1 is equal to V2. So this is V2. V2 does not need any information at all. And then we determine whether V1 is equal to V2. If they are equal, then that means here, this part, we really do have the private key. So just straightforward calculations. Now, the goal is to calculate y to the r, r to the s. So this is V1. Y to the r, r to the s. So here's the tricky part. This r appears both on floor 1 and floor 2. It's a tricky way of manipulating these numbers. 这个它凑数字就真的凑得很妙。你这个 r 同时在1楼跟2楼出现，这就是他凑的 ，Elgamore 先生凑的。我到目前为止还认为这个东西是具有艺术性的。为什么可以凑这么漂亮呢？等一下我们看一堆东西就消掉。我也是觉得这为什么会这么巧？看起来没有什么啊，就只有几行而已。问题是它就是凑得很巧妙。来，我们看一下 r， 我们就要算这个东西。y 的 r 次方 ，r 的 s 次方是干什么的？等一下算算看。你知道 y？ So let's come back and see what y is. So what is y? Y is your part of your public key. So this is alpha raised to the power of a. Okay. So So y is alpha to the power of a. Okay, a is your private key. Private key is the index. Okay, 这个 a 是 private key。alpha 的 a 次方是 public key， 这个应该可以理解，因为这个就是 Diffie-Hellman 嘛。所以指数的部分是 private key， 然后呢，整个合在一起呢，已经那个次方是 public key。这 Diffie-Hellman 以及 Algorithmic encryption 都是这样子的啊，这是永远是这样，所有这种 discrete log 全部都是这个样，指数你不知道，你不知道它到底几次方会等于这个东西。Okay, so this is private key and this is public key. Okay, alpha raised to the power of a, and then let's take a look. We're calculating y to the r. Y to the r, right? So this is y to the r. Maybe I can use a different color to illustrate this. So y to the r, r to the s. Y to the r, r to the s, right? So this is y to the r. That's the reason why we have this ar. ar. 这个就会凑到这边，为什么跟 AR？ 它这个 AR 就是要对应这个东西，就是把它凑回来。好 ，AR。So this we have AR, and then R to the S. Okay, R is this, right? Alpha to the power of K. And then S is this. Now S is the tricky part. We put this S here. Okay, this whole thing. So this has this K inverse. This K inverse is here. So that's the reason why we want to have a K inverse. Because we want to cancel this k， 哎，你这时候的 s 是这样放，我们看一下 k 的k 的这个啊、哦，然后呢什么呢 ？hm 加 a 啊，你看这时候妙的，来 hm 加 a 啊 ，h 的 m 加上 ar， 那我们来看一下哈，这个时候你会发现为什么这个要 r， 然后呢这个要 a， 它就是凑的嘛，它就把数字凑出来嘛。来看一下 ，maybe it's better to, yeah, looks like this is better to illustrate. Okay, so what happens here? Because of this y to the r, we have ar, and then this ar appears here. Okay, so this AR appears here, and then 等一下哈，对，这是减的哈，minus HM minus AR， 减掉 AR， 跟拿红笔减掉，减掉 AR。So we have so this is a minus sign. This is a minus sign. Yeah, hopefully this can be easier to understand. Okay, yeah, it looks good. So, the reason why we have an AR here is to cancel the AR here. And then this part is the signature. This is your design. Actually Mr. Algamot's design. He can design it this way. So you just calculate this thing, no matter what it means. It doesn't matter what it means. The goal is to reach the final destination. Okay, so you can have this AR here to cancel out AR, and then you have this K inverse to cancel this K. So what you left? All you leave here is HM. HM, which does not require any other information to calculate. 这就还蛮巧妙的嘛，所以呢，因为你现在 y， 你这个 y 是 public key， 所以简单的说，它设计是这样，你现在已经在具有 public key 的这个条件之下，你去计算这个东西，你计算这个东西，然后呢，跟你在这个 signature， 它在设计的部分就故意设计好，要把你这个 AR 给消掉。也把你这 k 的 inverse 给 cancel 掉，设计到最后，你计算出来的东西，实质上你计算就是阿法的 hm 次方，刚好让你的具有你现在这一边的计算，先走到 s， 再走到这个 v1， ，M 这一边的计算，第一步是你一定要从 public key 开始出发，你要从你只能从 public key 算嘛，所以这部分限制了这个你限制只有从 public key 的计算，但是这个计算算出来是刚好把一些不相干的东西全部通通消掉，最后你只需要 h 的 n， 你就可以相等。所以说为什么它两边它会相等？是 v1 等于 v2， 因为你就实质上根本就是等于阿尔法它的 hm 次方 ，hm 次方跟任何其他 t 都没有关系。两边相等的话，那就可以，其实就是这种，它就凑得很漂亮。我觉得这个凑的是真的是很漂亮。这个凑得漂亮不是只有我认为凑得很漂亮，后面 DSA 现在的标准就是因为学的这一招实在是凑得太漂亮，但是它还会把它扩展到两个不同的 group 上面，一个 group 跟一个 subgroup， 我们在后面再讲。So this is a really, I would regard this as a piece of art because this is really it's not extremely complicated, but it's a little bit counterintuitive, and then it really has two different ways of calculation. So one is straightforward calculation without any keys at all. The other is you have to have the first step and the second step. So the first step requires private key. The other one, the second step, you don't. Okay? Maybe we could take a look. So the first step, the signature generation. In order to calculate this S, which is the signature, you need the information of the private key A. That's what you need. So you need this information. But the verification scheme, this is the verification scheme, does not need this A at all, because this A can be derived from the public key. Okay. So this is a piece of art. This Elgamal signature scheme. Okay. Security. Security is also very similar to those discrete log problems. So later we will also, when we talk about elliptic curves, it also, this can be applied to elliptic curves as well. But we need some modifications later we'll explain. Okay. And then let's take a look at some characteristics. Number one, K must be unique for each message, right? Because for each message you have a K here. Let's take a look at what this K is. So for each generation, key generation, you generate a random number K. Okay. So which makes this signature even more difficult to crack because it involves a random number. So you will have different signatures for the same, even though your message is the same. But every time you choose a different K, then you end up with a different signature. So that is why this security is much better. Is better than RSA. The RSA does not have this thing. RSA does not involve anything not related to a random number. Okay. So as we can see, there are a lot of discrete log problems that are like that. When you generate something, every time you apply to the same message, if it involves in generating a random number, then it's going to be much difficult for the attacker to find any relationship between different messages. Okay. So anyway, this K has to be unique for every message, every signature you generate. No matter what message it is, you choose a different K. In this way, there's no way to keep track of those, and then you will violate the homomorphic property. So you don't have any homomorphic property at all, and no relations at all. Okay. So that's the idea. And then if existential forgery attack if a hash function is not used, if you just use m1, m2 directly, then extension forgery can be attacked. If you use the same key, you have existential forgery, even though it's not homomorphic problem, but you do have an existential forgery. However, if you choose different k, here you have k1 and k2, then it's not possible. So this is a really good property. Let's take a look at performance. Okay, signature generation is one modular exponentiation, one Euclidean algorithm. Okay. Verification is it takes longer, 3 modular exponentiations. Yeah, we can count. Generation, one modular exponentiation. Okay, and then one inverse. Here, there's no big deal. Multiplication. Subtraction, so it's no big deal. So generation is fast. Verification, y to the r, one modular exponentiation, r to the x, another one, and then alpha to the h and three modular exponentiation algorithms. So the verification is slow, but the security is much better than RSA. So that is that's the idea. And then we can also apply the same thing. Elliptic curves, then we can have a Algorithmic signature on elliptic curves when we talk about elliptic curves. Now let's take a look at Rabin. The Rabin is also very similar. Okay, we have so we know that Rabin is an expert in finding square roots, right? Quadratic residues. He almost dedicated his entire life on related subject. Miller-Rabin, you guys remember the Miller-Rabin primality test algorithm? It's also related to the quadratic residue or something, right? And others, right? So anyway, the signature is a quadratic residue. But you have 4, right? You have 4 signatures. You have 4 square roots, right? Quadratic residues. You just choose any one. That's it. So signature is, so this is also quite interesting. It has a main advantage. The verification is extremely fast because it's just a plain square operation. So the signature generation is slow, but the verification is extremely fast. Compared to algorithm, generation is fast, like 1 modular operation, but the verification is 3 modular exponentiation. So it's the exact opposite. Okay. But we have a problem. I said earlier, like if a man can have up to 4 wives, that means roughly only 1/4 of the men don't have wives, right? It's fair. 对，所以千万不能认为说一个男人娶4个老婆是件好事，绝对不行。我们从统计的观点来看，这对男人一点好处都没有。你怎么知道你会有钱呢？对不对？所以不要被误导了。然后从统计的观点看，1/4的 message 才会有那个平方根嘛。对啊，所以说呢，那怎么办呢？那如果没有平方根怎么办 ？So what happens if it does not have a square root? Well, it has to be modified by doing proper padding. So you add some padding at the end and see whether you will have square root. But the thing is, we don't know, right? So in practice, what we do is we can append a small amount of random bits. And then those bits, when we verify, we ignore those bits. So this can be applied. Okay. So, for example, the last 10 digits, for example, last 10 bits. If you do that, apply those last 10 bits. So this is your original message, and then last 10 digits are not used. We can call them don't care bits. Okay. We just append at the end. This is just kind of like a random string. And then if anyone has a square root, then we can use it as a signature. Okay. On average, 2 attempts would be enough. So just try. If it does not have, then you try it. Right? So 2 attempts. Right? So such method has no guarantee of success. Okay, so we cannot guarantee that a signature will always exist. Okay, so a deterministic method would be preferable, and then it does exist as well. So there is indeed really something called the modified Robin signature scheme. Okay, so they are mathematicians. Also, there are some mathematicians dedicated to this topic. So they apply some appropriate coding, and I think you can prove that the square root always exists. Okay. Actually, these are what mathematicians are doing. 这就是工程哈，这就是工程师跟数学家的差别。数学家呢，其实就很关心这事情。你要是没有平方根怎么办？就没有 signature 嘛，对不对？但是工程上呢，我们知道工程上你所有的东西只要看这个东西，只要错误率10的负5次方就好，我只要控制在10的负5次方，没有，我当做 fail 嘛。所以说哈，工程上你千万不要想去把错误率从10的负5次方降到10的负6次方，不要干这事情，千万不要干这事情。对，因为你这样的话，比方说你一个手机可能要卖20万，然后就没有人会买了，那这个这个东西就等于没用，你不服这个 cost 的这个，对啊，所以工程上完全都是要算 cost 的嘛，对不对？基本上是这样子。这就是为什么，对，这就是我觉得大家都认为这个标枪飞弹很厉害，对不对？标枪飞弹确实很厉害，但是我现在发现真正的杀手锏是什么？是 N漏更厉害。这个我会刚才讲这个东西啊，标枪飞弹它厉害在哪里？大家有知道它那个标枪飞弹啊，好，它是可以射后不理嘛，就是你只要2个人，你射出去了，然后呢，你基本上不用管，它命中率非常高，93%、94%，非常可怕的，步兵就可以把坦克干掉，很厉害没错。可是标枪飞弹1颗23万美金，也不错了，一台坦克大概200万美金，所以你大概是1/10价钱就毁掉人家一台坦克车，主坦克大概是这样子。可是那个 N 漏哈 ，N 漏它厉害的地方是什么 ？N 漏1颗2万美金。然后呢，重量呢一半 ，N 漏2万美金，重量一半。那它2万美金呢？哈，你1颗标枪的成本等于10颗 N 漏哎，这个开玩笑啊！1颗2万美金打你200万坦克哎，你不说这才是可怕。那它到底钱省在哪里？标枪有红外线巡标系统 ，N 漏比较没有。对，那你因为这个 trade off 的关系，你要多瞄准4秒钟。然后你的射程短一点，但是大家简单算一下啊，你今天打一台坦克，你射程比方说是2公里，缩成大概1公里半之类的，然后你多瞄4秒钟，可是你是1/10的价钱，你想想吧，哪一个厉害？对，所以控制这个成本是非常重要的啊。那他把这个红外线巡标器一旦省掉，那其他的部分他其他部分没有省，他把等于说，这种设计的思维是把一些不是绝对必要的东西，你牺牲一点 performance， 好，然后你多瞄4秒，你的命中率一样可以达到90%几啊，命中率差不多，价钱1/10，好，射程短一点，然后还轻一半哦，所以你扛1颗标枪飞弹，你可以扛2颗 N 漏，哇，这个就真是差很多，你身上一个人就身上可以背3、4颗 N 漏，那你说这个的话，这个成本就真的你如果按照这样算下去，对不对？那个你坦克再多没用，你这么便宜就跟你去打，所以为什么那个弹簧刀更可怕？弹簧刀实在太厉害，弹簧刀那个自杀无人机，1颗弹簧刀6000块美金，你看只要6000块，然后打那个200万的坦克，对啊。所以我觉得未来哈，这种弹簧刀，不知道可能不是每个人都知道。我跟你讲，它厉害在哪里？一个弹簧，它有2种，一个叫300的，一个叫600的。 300呢是装那种比较轻的炸药，一颗只有2.7公斤，2.7公斤，它几乎快要跟我的笔电一样轻。然后$6000美金，你一个人可以带多少颗？然后带多少颗？你带回去它就是一台无人机，它可以帮你，它上面有镜头可以去搜寻目标，然后找到目标之后，它可以从无人机直接变成一颗巡弋飞弹。它一锁定的话，它就无人机，它介于无人机跟巡弋飞弹之间。锁定目标，它就自杀变成巡弋飞弹，而且它自杀变成飞弹的时候，它的翅膀还可以收起来，就真的变一颗飞弹，然后速度很快。这种东西，这个东西哈，美国自己都挡不了。它这个2.7公斤，这个是打人的，专门暗杀用的。所以你只要有个人，他用轻量的炸药就可以把你炸死。它的范围是10公里耶，10公里。我们今天发射这个无人机丢那个弹药丢出去，然后你在那边就像打遥控一样去看有没有目标，有没有目标？有目标的时候，锁下去就不要管它，再打下去它就死掉了。这就为什么可以暗杀很多人。这个东西它飞得很低，然后它又很小台，你根本挡不了啊。所以为什么美国不敢给？之前只给英国这个国家，这个东西美国自己挡不了，而且它太便宜了，$6000美金。那还有一个600系列的是，600系列是可以打坦克的啊，但是就蛮重的。600系列就是快20公斤，然后但它是40公里，它就可以直接打坦克。所以这种东西非常厉害，所以这种东西是无解的。所以也不敢给太多，给太多的话，美国人的政要可能会被暗杀掉。以后就你躲在一个地方，然后你们按遥控，要看谁把它干掉就好。目前没有任何办法可以挡住弹簧道，这是没有办法的。所以这可能也是我们未来的研究方向，通讯所可能的一个研究方向。因为我个人认为啦，能挡住无人机的只有无人机自己，你别人任何东西都通通挡不了。对啊，那你也不可能拿那个你的防空系统，就像你爱国者3型飞弹，一颗飞弹就2亿，那你一台$6000美金，你拿这个去打，而且你打不下来，因为它太小了。所以这种东西是真的是现在这时代完全不同。So anyway, this is so the rapid verification is extremely fast. Okay. And then also cracking the signature scheme is provably secure. It's as hard as doing factorization, just like the rapid encryption algorithm. Okay. And then disadvantage, a system can only generate a signature for a single user, which is actually, I don't regard this as a disadvantage, because the reason is, RSA is like that too. Okay. So, for example, if you have let's see, if you have a group of many people in an RSA signature scheme, every person has to choose different P and Q. It's not like you choose the same PQ for all users and then each user, okay? It's not like that. Let's say you have the same PQ for example, for 10 users, and then each user just get a D. That's not possible because each user has to generate a private D, right? And then from this private D, you generate E. But the thing is, in that case, you need PQ, right? It's totally, it doesn't make any sense to share this PQ with among different users. It doesn't make any sense. So in other words, even though you have 10 people, each person chooses different PQ to generate different D. Okay, so that's the same. So I don't regard this as a disadvantage. Okay. Now let's move on to the DSA signature. So DSA, So the DSA signature is an enhanced version of alcohol. So we just take a little. I just cover a little bit, give you guys an idea, and we will maybe talk about this next time. Okay, because this is really similar. So the DSA algorithm. Maybe I can give you guys some intuition. So we just covered the algorithm encryption scheme. Now, DSA. So the idea is they want they want to choose a subgroup from a bigger group. Okay, so that's the idea. So if you choose a subgroup in a smart way, then it's you can actually have the advantage of a bigger group, which is more difficult to crack. But you need less number of bits to represent it. So that's probably the basic idea. So let's say we can choose. First, we choose a big prime. Okay. So first we choose big prime P, and then we have the ZP star, right? Okay. So big prime P. So this is prime. And then in ZP star, we need to choose a generator. So then we choose a generator. The generator is maybe alpha or something. Alpha is a generator. So alpha is a generator. So instead of directly working in this group ZP star, they actually try to work in a smaller subgroup. So in practice, because you're working in a smaller subgroup, you can choose this group to be bigger, and then because you're working in a smaller subgroup. So we know that this must have subgroups, because if P is prime, then we know that P minus 1 must be an even number. So an even number cannot be primes, right? So we don't have some factors. For example, what we have just seen earlier, we have Z13, right? We have Z13 star, right? Which has 12 numbers. So starting from we have a generator, which is 2, right? So we have 2 to the power 0, which is equal to 1. And then we have 2, which is 2 to the power 1. And then 2 to the power 2, and so on and so forth. And then it goes 12 steps. It will go back to 2 to the power 1. So this is 2 to the power of 11. Okay. So it's almost like a clock cycle. Yeah, clock arithmetics. So when you go from one power to another, it's multiplied by 2. It's kind of like you have, this is 12 o'clock, 1 o'clock, 2 o'clock. Okay? So the thing is, you may have many subgroups because you go 12 steps. Every time you go 12 steps, you go back to the origin. If you go each step, if you take 2 steps, for example, then you end up with a subgroup of 6 elements. If instead you go 3 steps, okay, 3 steps in each step, each giant step, then you have 4 elements. Those are subgroups. So each factor of 12 corresponds to a subgroup. 所以每一个我们刚刚的例子12步走回原点，1圈12步。如果你每一步是走你每一个大步是2步的话，那你6步就回到原点，那就是一个 subgroup 啊。那你 subgroup 就是你里面的 element 就是一半，因为你一个大步就是2步，那一个大步如果3步的话，你就4步回原点，对不对？那还有一个大步有4步的，你就3步回原点，那基本上是这样子。所以它会有一些 subgroup。那这个 DSA 呢，它的想法其实就是这样，它就是找一个 subgroup， 就是小一点，然后呢，它几乎是把这个 algorithm 全部搬上去啊，它非常像，在后面看一下就知道，它是非常非常像，特别是什么 HM 加 AI， 那 K inverse 几乎一样，但是它把它操作在一个 subgroup 上面，所以原本大的 group 变成小 group。那为什么要变小 group 呢？它其实目的是为了要让它的小 group 挑的比较好。那你在小 group 挑选一个比较好、性质比较好的小的 group， 它其实可以具有更大的 group 的优点，但是你可以用比较小的 group 的小的变数去表示它。大致上是这种思维的哈。好，那剩下细节我们下次讲。So we'll leave the details next week, and let's stop here.